observations are much shorter than this. A typical observation with Chandra is about 40 kiloseconds. So what does that mean practically? Well, in a day, there's 86 kiloseconds. So a typical Chandra observation is about half a day. These are, among all Chandra observations, these are by far the longest. Because if you want to study the distant universe really, really well, this is the kind of exposure that you require.
We're in the kilosecond range.
Well, these are in the megasecond range.
Well, those are.
These are mega, typical observations like 40 kiloseconds in round numbers. Your typical observation like half a day with Chandra. These are off scale. That's what we call the deep field. I need to deep. I mean, these orbs are very, very long. Get very sensitive data. That's what the deep there means. Yeah.
Just trying to bring in a sense of, for instance, the Hubble Deep Field. There was quite a controversy among the scientists involved as to where to point the telescope for something this long. I mean, you're dedicating millions and millions of dollars towards one location.
Right.
How did you make a choice like this? What's the thing you would look for?
Yeah, I'm going to show you that in just a minute.
Okay.
I have the answer. The answer, I'll just tell you briefly, is we chose these regions of sky that have the best data, not only at the X-rays, but across the electromagnetic spectrum. These are two favored regions of sky. One in the north, one in the south. So the best multi-wavelength facilities, either the northern hemisphere or the southern hemisphere, whenever they want to do a deep survey, want to spend a lot of time doing a deep survey, they pick these patches of sky. So these are not only have the best X-ray data, they have the best data in the ultraviolet, in the optical, in the infrared, in the submillimeter, in the radio. Across their spectrum, these are the best fields. Because we can use all that data together to figure out things better than any single wavelength alone. That's how we pick them, yeah.
Do those fields overlap with either any of the Hubble?
Yeah, they do. Yeah, they do, that's right. Yeah, the Hubble Ultra Deep Field sits down in the middle of this one, for example. That's right. That's how, one way we picked it.
Half an hour or so, just so you're knowing how long.
Fine, half an hour right now, that's
Yeah.
fine, yeah, keep going. Well, I think we're doing okay. Okay, so, right, I want to go through, I'm going to show you another nice example. So these are examples of, again, narrow sky region, very, very long observations. That's one way to do a survey. That's not the only way to do a survey. There's other good ways to do surveys too. Another approach, which other people have taken, is to not go as sensitive as these, but to cover a much larger region of sky. People do that as well. Here's an example. This is the famous Cosmos field. Okay? Here they didn't get nearly as long an observation as you asked. Here the typical observation depth is about 70 kiloseconds. So that's somewhat less than a day. But instead of covering a region that's only 60% the size of the moon, like we did here, they're covering 2 square degrees. Okay? And you get lots and lots of sources by covering those very wide fields for lower sensitivity. In this case, they have 1,887 sources. Again, most of those are growing black holes. Okay, so what we then do to figure out things about black hole growth in the universe is we combine together the information we get from the ultra-deep fields with these fields and with all the other fields we can do to get a complete picture of black hole growth. And this is a technical plot, which I won't go into as to that, but you get the idea. Okay, so then to answer your question a little further about why did we pick these regions? Well, we picked these regions because, again, they have the best coverage at all wavelengths, as I already said. Here is what I mean by that. The Hubble Space Telescope has surveyed the central parts of these fields, about the central third, to enormous depths. Some of you may have heard of the famous Goods fields. The Goods field north sits in the middle of the Chandra Deep Field north, the Goods field south is in the middle of the Chandra Deep Field south. So Hubble spent an enormous amount of time in these fields, and that's great, because that lets us go and study the galaxy morphologies for these growing black holes. Here in the infrared, the largest ground-based telescopes on Earth have obtained very deep observations in the optical and in the near-infrared. Here's a near-infrared image that obtained with the VLT telescope in Chile. Here are our observations with Spitzer, NASA's great observatory in the infrared, as an ultra-deep imaging of these regions. In the submillimeter, ALMA now is getting fantastic data in the submillimeter band on these fields, letting us, as I'll talk about later on, discover galaxies in the process of formation. In the radio, the VLA telescopes located in New Mexico have obtained very deep radio observations over these same fields. And so that's why we pick these fields, and all this multi-wavelength data works great together. Because it lets us, from my point of view as an X-ray person, it lets us identify the X-ray sources, it lets us figure out what they are, it lets us measure properties of their host galaxies, like how massive are the galaxies in which black holes grow. How fast do stars form in the galaxies in which black holes grow, and so on. All those things are critically important for fully understanding the sources that we're detecting. And so that's why we chose these regions. And I also want to highlight the large amount of spectroscopic work that's been done, where people have used the largest optical telescopes on Earth, Keck in Hawaii, the VLT in Chile, Subaru also in Hawaii, to get spectroscopy of all these X-ray sources, to actually measure redshifts and determine how far away these sources are. And that's been extremely important for just figuring out the nature. Until you know how far away these things are, it makes it very hard to figure out much about them. So over the past 17 years, there's been an enormous amount of progress using the multi-object spectrographs. And here I'm listing the names of the multi-object spectrographs on these telescopes that have been used to do the work. But this remains a challenge, because many of these X-ray sources are very faint. So this is still a bottleneck. And so some of you probably have heard of the fact that people aren't satisfied building these ones this big, and people now want to build 30-meter telescopes, or 50-meter telescopes, or even bigger telescopes. One of the reasons they want to do that is because we still have challenges finding and getting redshifts for the counterparts of all these X-ray sources. And so that's one driver of many. There's many drivers, but this is one big driver for the construction of even larger ground-based telescopes. Yes?
How difficult is it to get a redshift? You have
Hard.
galaxies moving away, you have one side going almost light speed away, and another half of it coming at you.
Well, the galaxy, remember, the galaxy itself
And
is
then
not,
what if it's on an angle, you know, the disk is
yeah.
facing you.
Right, okay, so the galaxy is not rotating at anywhere near the speed of light. The region close to the black hole rotates near the speed of light. The galaxy, more broadly, is moving in a much more stately manner. And so that isn't a problem. What is a problem is the fact that these galaxies can be very faint. And I'll show you, going back to the Hubble Deep Field, or one of these examples, I'll just show you the good image here. I mean, we have X-ray sources in nice bright galaxies like this one, and we have X-ray sources in little splotchy specks like that, and we have X-ray sources in things so faint that you can't even see them on this picture that I've drawn here, and you can only detect them statistically by doing an image analysis on the data set. And so the challenge is many of these sources are so faint that even an 8-meter telescope has a hard time actually getting a spectrum to determine how far away it is. Yeah.
Can you just kind of explain a little more for the audience the redshift concept? Just
Yeah, okay.
briefly.
Yeah, briefly. Okay, so the way, have some of you, many of you have heard of the concept of redshift. Okay, so people, owing to the expansion of the universe, galaxies are moving away from us in this grand cosmic expansion, okay? And we have worked out a relationship between how big the redshift of spectral lines is and how far away a galaxy is. That's the famous Hubble law that some of you may have heard of. I mean, you've heard of this guy Hubble, the guy the Hubble Space Telescope named after. Well, he must have done something pretty good, right? That's what Hubble figured out. He figured that out, and he figured out as a consequence the universe was expanding. And we used that Hubble relation, worked out by Hubble back in the 1930s, to get the distances. That's the basic idea of how we use spectrum and get the distance between these. Okay.
I'm sorry.
Yeah, go ahead.
In other words, the farther away, the redder,
Correct.
if I recall.
That's correct.
Farther away.
The farther away, the more shifting of the light toward the red.
Right.
And we use spectral lines, where we know the characteristic barcode pattern that a galaxy should have, and we recognize that barcode pattern, but just shifted redward. And so it's like reading a barcode at the supermarket. That's essentially what we're doing, if we're doing it for galaxies.
And distance equals age. You're
Yeah,
looking
distance
back.
corresponds to age, that's right. When we look at very distant galaxies, we're looking at galaxies as they were long ago. Okay, so now I want to talk to you about some selected science results. Okay, So far, I've been telling you a little bit about all the machinery. I've given you an introduction, I've told you about doing the surveys, but what have we learned from all this stuff? What's the intellectual payoff of doing it? Well, there's a couple things. Okay, here's one of them. And this will be slightly technical in places, but it still should be quite clear, and I'll try to throw in a few jokes to make it happen. Okay, so one thing that we have known for a long time is that the population of active galaxies evolved strongly over the history of the universe. Okay. And here is a technical plot showing it. For those of you who are technical, showing redshift versus the density of luminous active galaxies. Here is the one that I teach to my Astro 100 grads at Penn State. Okay? And this one is actually more useful in some ways, okay, for being understandable. What it's showing is it's showing the density of luminous active galaxies, the so-called quasars, which are the most luminous active galaxies, versus cosmic time, where the Big Bang is over here at time 0, and we are living today over at time 13.8 billion years over there. And what do you see about the population of quasars over cosmic history? It peaked a long time ago. That's right, it peaked a long time ago. Okay. And we have known this for a long time. We've known this since the 1970s. So this isn't new, but I'm telling you, we've known for a long time. Since the 1970s. What we have known since the 1970s, that luminous quasars peak strongly out at redshifts of 2 to 3. Or speaking in another way, there was an era of the quasars. It was a few billion years after the Big Bang. Okay? And during that time, quasars were 1,000 times more common than they were earlier and than they are today. 1,000 times more common. So the population of quasars has evolved enormously over cosmic time. And if I could have picked any time in history when I would have wanted to live, I would have wanted to live there. Because I could have walked out of my backyard and looked up in the sky and seen quasars with my naked eyes. Okay, you could have walked out and looked up at the sky. You could see growing supermassive black holes with your eyes because they were so common. You would just see them out there. Okay. So the point here is that the population of quasars evolved tremendously. It's the same way that demographers of people on the Earth measure how the population of people changes over time in various countries. It's the same thing here. Quasars have had this enormous change over cosmic history. And this is both fascinating and depressing for someone like me. I mean, it's fascinating that it does it, but it's depressing because we missed the party. Okay, see what I mean? You know, the universe had this enormous party back here where there was tons of black hole growth, where there were tons of active galaxies, which again represent growing supermassive black holes. And we're there today, and we're just seeing a little bit of confetti that left on the floor. Okay? And when I tell this to my Penn State undergrad, they get very upset, because you all know Penn State undergrads don't like to miss a party. Okay? And so they tell me to get to work and fixing it. And I'm going to try to tell you how we actually fix this and we make the Penn State undergrads feel better. That'll be my next one.
Are quasars and active galactic nuclei the same thing?
Yes. Quasars are the most luminous examples of them. They're the ones that are easy to study even when they're far away, just because they're so enormously powerful. That's why it was possible to study the quasars back in the 1970s. Okay. It took something like Chandra to take us to the next level of understanding, which is what I'm going to show you the next overhead. But right now, I just want to lay out the quasars very clearly. Does that make sense?
Yes.
Say, okay. Any other questions? Yeah, go ahead.
Yeah, I thought when you started this presentation that you were heading toward all the mass in the universe being in black holes. But it looks like because of this curve you just
They
showed
stop.
us that it will stop or nearly
Well,
stop.
but I'm going to tell you, it's not as bad as you think. Wait for my next slide. I'm going to reveal a fuller understanding of things that we have on account of Chandra. Right now, I'm just setting the stage. The next overhead is going to be the one that actually shows what we learn now.
So do you think we're headed toward?
Well, just let me do the next slide.
My question, I guess it sounds simple-minded,
That's
but you
fine.
said that you would have been looking up in the sky and seeing them.
Yeah.
What did you see? I mean, what is up there then?
But when we look out at the sky now and look up, you see stars. You see
Right.
stars in our galaxy.
Right,
The quasars today are so rare that you don't see them with your naked eye. It takes very deep telescopic observations to be able to see them.
but if you did see them, they were so common, they were right over.
Back then they would have been. Yeah.
What would you look like?
What do you see glowing? You see these fantastic blue glowing objects up in the sky. They would look star-like, they would look like stars, but they would actually be growing supermassive black holes.
Right, and it'd be common.
They would be common,
Wow.
that's right. They'd be 1,000 times more common than they are now. Plus, the fact the universe was smaller back then, which makes it even better. Okay?
Okay.
Yeah, go ahead.
Is there any reason that spike could occur again?
It's probably not going to occur again. And that comes from understanding where the spike came from in the first place. And let's sort of guess. I mean, I'm sure people in this audience can guess the origin of this. Let's ask this. Why weren't there quasars right after the Big Bang? Why weren't there quasars 10 seconds after the Big Bang? What?
There was no mass.
So there was mass, but the mass hadn't concentrated down yet into galaxies. There weren't galaxies yet. It took a while. It took a while to build galaxies. And you need galaxies to be able to build black holes. So back here, the reason why there weren't quasars back then is because galaxies hadn't been built. But after you build galaxies, the quasars came in very fast thereafter. Now, does anybody want to guess what happened here? Why did they stop? Why do populations die off on Earth?
Expansion.
Go ahead.
Run out of food.
Sucked up all there was to suck up.
That's right. They run out of food. They run out of food. They sucked up all the food. They had their feast. They ate up all the stuff in the center of galaxies, and there wasn't any more to eat. And so the black holes didn't go away. The black holes are still there, but it's just they declined in activity, so they're no longer around. Does that make sense? So that's the origin of that. And we've known that since the 70s. Okay. Now again, we're going to go back to trying to make the Penn State undergrads feel better. Okay? The point is that the quasars tell you this depressing story that we missed a party. The universe had this huge party. We missed it. Too bad for us. But the problem is with this entire branch of study, until we had something like Chandra, is that we were only studying the quasars. These are the rare one in a thousand most powerful examples of active galaxies. They do not tell us how most active galaxies evolve. That's what I'm going to tell you about what we figured out from Chandra. Okay, and that's what this slide means. This is a technical slide, a little technical, but it should be understandable. So now I'm showing this as a function of redshift. Redshift 0 is where we are today, and as you go in this direction, you're moving to greater and greater, more distant objects. So always you're at great distances, okay? And what I've done in this plot, and here I'm showing number density again, and what I've done is I've color-coded these curves. These are the most powerful active galaxies we find now using Chandra-based X-ray surveys, where we can find all the active galaxies out there. These are somewhat less luminous, somewhat less luminous still, somewhat less luminous still, somewhat less luminous still. What do you see as you move to less and less luminous populations in terms of where they peak? Someone tell me what you see from that plot.
Closer to now.
They peak later and later in cosmic time, don't they? The most powerful objects, entirely consistent with what people have known since the 1970s, peak are creatures of the distant universe, as we know. But as you go to less and less luminous objects that you couldn't find before you had the Chandra surveys, as you go to these less and less luminous, we find they peak at later and later cosmic times. Okay? And that's the point. Lower luminosity active galaxies peak at later cosmic times. This is a remarkable thing for a number of reasons. First of all, it's totally anti-hierarchical. We normally think of structure of the universe starting small. You build some little things, the little things merge together and make a bigger thing. Those merge together and make a bigger thing still. So you start off small and go big, right? This is the opposite. The big things came first and the little things came later. And that's because you're moving through many generations, likely thousands of generations of quasars turning on and off, or active galaxies, turning on and off, on and off, on and off. And this is the superimposed pattern of all of those put together. So that's how you get an anti-hierarchical behavior. And the point is that unlike what you would have expected from the quasars, where the bulk of supermassive black hole power production is out of the redshift of 2 to 3, very distant, we think it's now more of a redshift of like 1 and 1.5. And the lower luminosity systems are peaking at even later redshifts still. And so the point here is that we didn't entirely miss the party. Okay? We didn't miss the party. The Penn State undergrads can feel better. Okay? The party just shifted to smaller and smaller scales. Okay. the huge sort of campus-wide parties indeed happen in the distant universe. But the smaller sort of frat house or sorority house parties are still happening today. And that makes the Penn State undergrad much happier. Go ahead.
Is that because as the universe expands, could it be?
I have to do this because I teach this to hundreds of Penn State undergrads.
As the universe expands, it takes longer for everything to get to it, to be sucked in?
I mean, why is this happening?
No, I'm saying, could it be happening, so it takes longer for the material to get to the black hole because everything is getting bigger and bigger and bigger and bigger?
Yeah, we don't think that's the cause. We think the cause has to do with how galaxies use their gas. What do I mean by that? We think that the most massive systems, while they have more gas to start with, they use it much more flagrantly. And it gets gobbled up very quickly. Whereas the lower mass galaxies are much more stingy in how they hold on to their gas. And that lets the black hole activity occur later and later in cosmic time. And the technical reasons for that come with studying the technical subtleties of diagrams like this. Okay. That's the overall answer. Yeah, go ahead.
Stars also.
Stars behave that way as well, exactly. That's analogous to what stars do. It's not the same physics, but it's the same idea. You probably know that massive stars, even though they have more gas, live shorter lives than low-mass stars. Well, it's the same type of thing happening. It's because behind that, even though they have more stuff, they burn that material more flagrantly. And that's what makes them last less time than the low-mass stars. Well, it turns out galaxies and their supermassive black holes have a similar behavior to them. And that's what Chandra taught us. Okay, so that's one example of what we learned. So we act like demographers, census makers of black hole growth in the universe. Okay, the one yes, okay. So now I have to tell you about this point. Okay, so again, the point here is that, again, these curves represent the production of enormous numbers of black holes over cosmic time. While the black holes may shut off and no longer be active, well, the black hole itself doesn't go away. So you can ask the question, where are all these black holes? Where are they now? The same question we asked about movie stars and got the answer to recently in the new Star Wars movie. So where are they? Well, as I've already alluded to, we now know where they are. There are local galaxies around us today. You look at the center of our galaxy. The center of our galaxy is a 4 million solar mass black hole. That black hole had to be built. At one time in the past, we were in one of these systems. At some time in the past, we built our black hole. We once lived in an active galaxy. We no longer do. Okay, and this is the same thing in general. Here's the plot just showing examples of galaxies. Here's many galaxies. Here's one here. Here's the full image of the entire galaxy. That's a Hubble Space Telescope image of the very central region. This one has a 3 million solar mass black hole in it. Here's another one. Here's the galaxy. That's the central region. This one has a 20 million solar mass black hole in it. Here's another one. There's the galaxy. There's the central region. 200 million solar mass black hole. There it is. Here's an even bigger one. The 2 billion solar mass black hole. That's that big circle there. Okay? That's that one. What do you notice about the relation? Do you see a relation there?
They really start to blow up as they get heavier.
As they get heavier, sure. They get bigger as they get heavier, for sure. You notice any relation between the galaxy property and the black hole property? Well, do bigger galaxies have bigger black holes or smaller black holes? Bigger black holes. You can see that just from that diagram, and that holds more generally. And this is a remarkable thing, and I want to tell you about that. Okay. Here's what I want to tell you about. This is going to be the role of active galaxies in galaxy evolution. What you just noticed from that previous diagram holds more generally. And this is a truly amazing plot. It shows the mass of the black holes in centers of galaxies versus, in this case, the velocity dispersion of the stars in the galaxy's bulge. So we know the galaxies have bulges. Here are two famous galaxies. This one and 104, the famous Sombrero galaxy, that's the galaxy's bulge. We measure how the stars in that bulge move, which tell us essentially the mass of the bulge, and we find this amazing relation that I just showed you between the mass of a black hole in the center bulge of the galaxy and the mass of the galaxy bulge. Here's the correlation. It holds generally. This is an amazing thing, because again, as I've talked about, the black hole is a rather tiny object, it's only the size of the solar system. Whereas the bulge, well, this is the enormous bulge of the galaxy. I mean, in terms of relative scales, this is if you took the galaxy bulge to the size of the Earth, the black hole would be the size of a pebble. Yet somehow the entire bulge knows about that black hole. This is an amazing thing that we don't fully understand, and we are trying to understand right now. The thing that makes it very challenging to figure out is that we are essentially studying in this diagram, we are studying the remnants of things that were once great. What do I mean by that? Well, when you look at black holes, the black holes we're studying and measuring masses for all these galaxies are dead black holes. They're hibernating black holes that are no longer growing. They're not active systems anymore. Okay? So it's kind of like studying the bones of the dinosaurs. They were once great, now they're dead. It's very hard to figure out a whole lot about them just from the bones. Okay. Similarly, along this axis, when we study galaxy bulges, like this one, or like this here, M87, where the entire galaxy is a bulge, okay, these systems, especially the bulges, are dead systems, in the sense that they're no longer forming stars. You probably know the galaxy bulges don't form stars very much. Okay, so that's the challenge that we face in a diagram like this. It's hard to figure out where this beautiful relation came from, because the black holes aren't growing anymore, the bulges aren't growing anymore, and so you're essentially studying dinosaur bones and trying to figure out things about the dinosaurs from them. Okay, what I want to do from these X-ray surveys, I want to go back to Jurassic Park, or now they call it Jurassic World, the rebranded movie, I guess. And I want to actually see directly the growth of the black hole and the growth of the galaxies, and we can do that. We can actually directly see these things together. And I want to tell you about our attempts to do that, and then I'll finish up. So I'm going to show you a movie now to sort of illustrate how this might have come about. That is, how did the relation between a black hole and a galaxy come about? How did the black hole, for example, influence the galaxy to shape it, set up this correlation? Well, here's a movie I'm going to show you. I'm going to be the next slide. I'm going to get you ready for it now. It's a movie made by a professor at Penn State, Yujing Li. She's a theoretical astronomer. She runs massive computer simulations to try to work this stuff out. And what you're going to see is a movie, and here are some stills from the movie. And essentially, the intensity of the shot is showing the density of gas in the system. And the color shows the gas temperature, such that the purplish gas is nice and cold, and the yellow color gas is very hot. And these black circles in there, those are the black holes, the supermassive black holes in these systems. Okay? And you're going to see a pair of galaxies coming in and merging. You're going to see them firing up the active supermassive black hole and then blowing gas out of the galaxy. So I'm just going to let the movie run. So here it's running. You have galaxies, sets of galaxies that are merging to form a single large galaxy. There they're doing it. Okay? Galaxies continue to merge. There are more galaxies coming in and merging, forming a single large galaxy. Okay? The galaxy is merging, it's setting itself up. Soon you're going to see the black hole firing up. It's starting to drive a powerful high temperature outflow from the system. There it is. See all that high temperature gas being produced by the black hole? You see how that's pushing out the cold gas? There it's firing up, becoming very bright, pushing out all the cold gas from the system. We think that type of phenomenon may be responsible for setting up this relation between black holes and galaxies. Okay? You're essentially, in a system like this, driving out all the cold gas. That cold gas is essential to feed the black hole and to allow stars to form. And by driving out all that gas, you essentially truncate star formation and you truncate black hole growth. And if conditions are right, and do it in a synchronized way, you can set up this relation between black hole properties and galaxy properties. So that's what we're trying to do theoretically. Observationally, I'm very excited right now about combining sub-millimeter observation and X-ray observation. So in particular, I'm interested in X-ray studies of these famous sub-millimeter galaxies that some of you may have heard of. But these are not little galaxies less than a millimeter in size. These are galaxies detected by their strong sub-millimeter emission. Why are they strongly emitting in the sub-millimeter? Well, it's because they have tremendous bursts of star formation going on in them. These galaxies are forming stars at about 1,000 solar masses every year. That's about 1,000 times the rate our galaxy forms stars. Yet they're optically nondescript because they're heavily extincted by all the dust in the system. These galaxies have now been identified using telescopes like the James Clerk Maxwell Telescope, which operated in Hawaii, and now ALMA, the Icon Large Millimeter Array, shown down here. And we find that these extremely powerfully star-forming galaxies are creatures of the distant universe. They typically exist at high redshifts of 1.5 to 3, where they're about 1,000 times more common than they are today. We have a few examples of such systems today, 2 examples are shown here, but they're much more common in the distant universe. Why are these exciting? Well, because we are seeing galaxies here building their bulges. Okay, I told you galaxy bulges are dead today, right? But they weren't always dead. In the past, galaxies had to build these things. These bulges just didn't spontaneously come into existence. They had to be built. Well, by observing these submillimeter galaxies, we are now actually finding galaxies in the process of building their bulges in the distant universe. We can actually see the bulge being manufactured. The submillimeter emission lets you home in on them. So the question then is, well, given that we have this remarkable relation between bulges and black holes, can we see the black holes growing too? And the answer is, yeah, we actually think we can. We're making progress on that right now. And we're combining together data from ALMA and data from Chandra to do it. Here's a nice plot from some work that my group has done, showing here X-ray observations. This is the X-ray image. This is the corresponding ALMA image. So again, this shows you there's a galaxy there building its bulge. This image shows you, and there's a growing black hole there too. Do you see? Growing bulge, growing black hole. Here's another one. Growing bulge, growing black hole. Growing bulge, growing black hole. Growing bulge, growing black hole. We actually find that a high fraction of these bright submillimeter galaxies are X-ray detected in the very deep surveys we perform. They often show evidence for AGN activity, such that 20 to 35% of these systems, which is a very, very high fraction compared to galaxies as a whole, have growing supermassive black holes in them. So this suggests a very high duty cycle for black hole growth in forming bulges. Every time you have a galaxy that's building its bulge, you commonly see a growing supermassive black hole in there too. So we actually hope now that we are directly observing the formation of this connection between black hole growth and star formation rate. And we're trying to quantify this and understand it further right now. And I'm just going to end with a couple of future prospects. We still want to have some big unresolved questions. We want to push to the even more distant universe to understand how the first black holes came about. We want to understand better, as I just alluded to, how black holes and their galaxy populations, how their black holes and galaxy stellar populations evolve, and we want to understand how large-scale cosmic environments shape black hole growth. We hope to answer these questions. Chandra, as I told you about, is we're still working great. This plot here shows the state of health of all the major Chandra subsystems. The details don't matter. The most important thing is that our current estimates indicate that both Chandra and XMM can likely last until 2025 and perhaps beyond. Okay, so we have a good amount of time. We can hope to conduct many more surveys with Chandra and XMM. These things were built to last. Okay, again, they were launched in 1999 and 2000. They may well be going